just before I start, this work has been done with a lot of people. So Peter, AJ, Aaron, Chen, uh, Sir and Dilip are at Google, and Philip and Yonglong are at MIT, and this has been a joint effort with them. And yeah, we have submitted this to NeurIPS, and we have an archive version available, which we will be updating as well. So the results in this talk are going to be from other contrastive learning work, supervised contrastive, and some results which are not exactly published yet, but we'll get there in a few days. So yeah, if you have any questions about those results, you should definitely ask them. Right. So basically, contrastive learning is this study where people have used representation learning in a context which is separate from the downstream task. And the basic idea which came out of theoretical work that was done by Sanjeev Arora at Princeton a few years ago was basically that you can pull samples which share class information, or they are different augmentations of each other, and hence you know that they are more similar than others together, and push samples which you expect to be different apart. And these could be various kinds of transforms that you could come up with, such as color transforms, crops, warping, Gaussian blurs, and so on. And all kinds of meaningful semantic information retaining transformations are useful. It also depends on your downstream task sometimes, but we can get into that later. So that's basically the idea of contrastive learning. So our goal was to understand why these work so well, and what's the basic principles which we can extract from that, and what are the use cases where this, what are the kind of downstream tasks where this works well. So this is kind of the work that came out in the last 12 months, which gained a lot of fame. Basically, there were these two papers. One was contrastive multi-view coding by people over at MIT, and the other was the paper from Hinton's group, which is simpler. Both of them work in very similar ways. So what you have on the left is that you take different color transformations and you actually reduce into various color spaces, just let's just luminance and maybe chrominance, or maybe various semantic segmentations, and then you embed them using separate encoder networks, but into the same representation space. So the representation space is shared, while encoder networks will be different. And you do this for a single image. So you have, let's say, 4 representations corresponding to one image, and then you try to push them together, while you try to push representations from any of these networks for a different sample apart. And so this is a completely unsupervised way of learning representations in a contrastive learning setting. Simpler had a slightly different view, where they took random data augmented versions of a sample, which was basically random crop and then color transforms, color jitters, Gaussian blurs, and they encoded them and basically pushed the representations of the two dogs together and the representation corresponding to different data augmentations of the chair together, but pushed the representation of the dog and chair apart. But this was not done using label information. Hence, they could have very similar looking dogs being pushed apart in the representation space. So before we go into more details, I just want to talk about how these techniques usually work. So the aim here is that the downstream task that is you evaluate on is still top 1 accuracy and labeling samples. So the way you do it is that you have a first stage where you actually do contrastive learning, and contrastive learning losses are actually applied in a small 128 dimensional space. So you have your encoder network, which actually gives an output of 2K, and then you actually project it down to something like 128 dimensions or 256 dimensions, depending on what your use case is. Apply contrastive losses in that space, train your network, and then you drop out the projection networks and use the 2K embeddings, that is the last layer of the ResNet in most cases, or efficient net, whatever is your encoder network. And you apply a linear classifier on top of that and try to do cross entropy training. So there's a first stage where you're doing contrastive learning, and a second stage when you're doing cross entropy learning. This is in contrast with standard cross entropy where you train end to end. And the benefit here is that these representations are independent of the label information. So you'd never use label information during contrastive learning. So the idea is that you should be able to use it for transfer learning and other downstream tasks without actually biasing your training procedure with using labels, right? So the form of the loss that is used in such contrastive learning setups is something that looks like this. So you have the total loss over the entire batch, and for every sample in the batch, you have a likelihood term inside the log. This likelihood term comes from the exponent of the similarity between the embeddings. So Zi is the embedding corresponding to sample I, and Zj of I is a data augmented version of a given sample in the batch. And you have the similarity between them as Zi.Zji. This can be generalized to arbitrary kernels if you want to, but in most cases, since you already have a projection network, you can assume that a kernel is being learned by that projection network. And then you so basically you exponentiate and you come up with this likelihood term. So this what this term is, it basically says that given the batch, what is the probability that J of I is the most similar sample to sample I among all the samples in the batch. And so this is not over the entire training data set, but for like large batches, you can say that, okay, this is an unbiased estimate of the likelihood in the entire data set. And well, maybe not unbiased. It's going to be biased, yeah. But right. So you have this log likelihood term which you are minimizing. So you're maximizing the likelihood, and this is what you use to train the entire network end to end. And you use all the other samples as negative. So negative is any sample that is not supposed to be similar to the anchor. So and a positive is a sample which is supposed to be similar to the anchor, and in self-supervised losses, that's just the single data augmentation of the given anchor, right? So but why should that work, right? And there are various papers which were doing similar things. And what is different about contrastive learning? Like triplet losses have been known, and Siamese network have been known, and like a bunch of other things have been known. Like energy-based models have been famous for a very long time. So the question is that what is amazing about this contrastive learning framework? And the answer is that contrastive losses are a lower bound on the mutual information between the views of the data. So given a sample, you have two data augmentations of it, right? One of them is being called the anchor and the other is going to be called the positive, right? And contrastive losses actually a lower bound on the mutual information between these two samples. So what you're technically doing in this entire training procedure is using this likelihood estimate to actually maximize the amount of mutual information between the two views of the data. And note that these two views are actually created arbitrarily by you. You are either doing color transforms or you're doing data augmentation or something like that. And you can do a lot of other things. Like for example, in videos, you could actually take different frames, right? So just having two views on the data, right? And actually maximizing the mutual information between them, and you have a lower bound for that. So you have the contrastive loss that can be optimized, right? And the byproduct of that is that you can show that the self-supervised loss, when minimized, actually also minimizes some version of the downstream classification loss. So under some regularity assumptions, like your downstream loss is going to be a classification loss, and it's probably going to be a binary loss or a categorical loss and so on, you can come up with a bound on that. If you actually minimize the self-supervised loss, you're going to get some multiplicative, it's not an additive bound, but a multiplicative bound on your downstream task. So which is a good thing, because it means that what you're optimizing inherently optimizes what you care about downstream as well, which is not the case usually, right? So this is why it works, and you can look into the details of some of the work that has been done, such as the work by Bachman and the work by Aurora, and these are great reads in themselves, right? So but all of that's fine, right? The question is that we tried this before, and a lot of formulations came out before. Does this work now? And the answer seems to be yes. Simpler basically made the claim that with a 4x ResNet 50, they are able to get as much as supervised performance, which is a great result. And there are arguments about, okay, why didn't deeper networks work, and why did wider networks work? But it is inarguable that self-supervised learning is getting very close to fully supervised learning. And uh, the question is that, can we push it further? Can we actually make contrastive learning work better than cross entropy learning, right? Because in the end, you're still only using label information in these self-supervised settings when you're doing actual cross entropy training of the linear classifier that is trained on the embedding. So you freeze the embeddings and now you're training linear classifier, but still being trained with cross entropy, right? So you did actually use your label information very meaningfully. You just use unsupervised part of your data. So that is where our work comes from. The motivation is that, could you basically take this entire line and just push it up, right? And the formulation we came up with was just going along with the way of thinking that we have in standard contrastive learning, that you have an anchor, which is, let's say, this cute dog, and then you have uh, an augmented version of the same sample, which is a positive, and maybe you have this other cute dog, which is also a positive for this same sample, right? So, and you push away all the other samples, such as elephants and cats and so on, which is not something that self-supervised contrastive does. Basically, self-supervised contrastive will also push away this specific dog from the anchor dog, which is not a good thing, because you actually want this to be like a smooth fall off, instead of like a very extreme fall off, that, okay, the moment you move away from a single sample, nothing has a very high likelihood in this 2k dimensional high dimensional space. You don't want that. What you want is that it's a smooth fall off, and the fall off corresponds to the actual semantic similarity. And label information, in some sense, is a good measure of semantic similarity. There are better ones, and more diverse labels also help, but uh, given what we have, label is definitely something that we should use, and this is how we're using it. It's still not clear how to do this perfectly, because we had this likelihood and mutual information kind of interpretation before, and we want to keep all of those without making things more difficult for ourselves. So what we realized was that there are multiple possibilities. One clear possibility is that just take out samples which correspond to samples from the same class being used as negatives. So do not push against them, basically. And does that work well? The answer is no. It does not lead to great boost in performance. And our running hypothesis that you actually do need to pull samples which belong to the same class together. And there has been recent work which shows that there are other ways to get around this. But our way was that you actually use them as positives, in the sense that samples from the same class, but which are not data augmented versions of the anchor, you pull them closer to the anchor instead of just not pushing them away, if that's clear. And the other contribution that we felt was very important in making this work was using stronger data augmentation to make sure that you don't now learn spurious correlation to labels, because that was one of the good parts about contrastive learning, that since you weren't using label information, you weren't picking up spurious correlations between your image data and the labels associated with them. So the idea was to have very strong data augmentation which gets around that. Right. So I'd just like to introduce what the loss function looks like. So the expression might be slightly hard to work with, but here's what it looks like. For a given anchor I, right, in the batch, you have a set of samples which are positives, which are denoted by P of I. So you normalize for the number of positives you have for a given sample. So you don't want that some losses are higher or lower because they just have more samples and more positives in the batch, because we're still sampling our batches randomly, and we don't want that it ends up that some of the sample, a large amount of the gradient comes from a few samples. Um, Right. The next part is that basically we again have a likelihood term, but this likelihood term is computed for every positive and every so for a given anchor, for every positive that exists, you compute this likelihood term very similar to self-supervised, where you have this dot product, which is supposed to be a measure of similarity, and then you exponentiate to get this likelihood term. And what we are basically saying is that we are minimizing the negative log likelihood of the sum of these likelihoods, right? And what's that's equivalent to saying that you are actually maximizing the joint likelihood of all the positives given a specific anchor. So that's the distribution that we are working with, right? The other possibility is that you actually take these likelihoods, you add them up, which is basically saying that, okay, you just have this conditional distribution and you're just adding all these likelihoods together, and you are going to maximize this likelihood together, right? And so basically you compute this likelihood and you keep the log outside. So the big difference when you look at the expression is that if the summation 1 by p of I is inside the log, which is this case, and or outside the log. And what our results suggest is that outside is better by a very big margin. And the insight there basically is something like this, that when you have it outside, a given positive, um, which is very far away from the anchor, has an equal contribution in the gradient as a positive which is very close to the anchor, right? But that is not true for when the summation is inside the log. And you can see this from the expression, because you have these probabilities getting added up, and you have a temperature parameter here. So when this temperature parameter is actually low, which is generally the setting that we have, then a large amount of the likelihood is actually concentrated on a few samples. So it will turn out that most of the magnitude of the gradient will actually come from a few samples in the second case, which is not optimal for training, because then you're not using your label information meaningfully, right? So this is the loss function we ended up working with. All the terms except the self similarity are in the denominator, and the numerator has the single term corresponding to the similarity between an anchor and its positive, and then you sum over all the positives. And just talking a little more about the loss function, because some people have this notion that there's something unique about this loss function, and our perspective is that while the interpretation of the loss function as a mutual information minimizer or maximizer is interesting, that is not what is training the model. What is training the model is the gradients, and we should be able to look at the gradient and make interesting observations. So one of the interesting observations that we have been able to make is that the gradient looks something like this, where the gradient of the embedding, gradient of the loss with respect to the embedding is something like, so we have 1 by tau term, which is basically weighing the representation which are coming from other samples. So it's weighing z of p, which is the representation corresponding to the positive, or z of n, which is the representation coming from the negative. And there is a weight associated with it. The weight is proportional to p of ip. P of ip is nothing but the term we had here. So this term inside the log, that is what we call p of ip, is basically saying what is the likelihood of the positive coming from the same class as the anchor I, right? So basically what we get down to is that the gradient looks something like the embedding multiplied by the probability, and then a correction term. This correction term for the loss that we actually end up using is 1 of p of I, which says that I will correct for all of those terms equally, and the amount by which I will correct is 1 by the number of positives I have in the batch. In the case when the summation is inside the log, it turns out that this correction term is a likelihood among all positives. So for all the positives, you have a correction term which is larger for the ones that are closer to the anchor, and smaller for the ones which are far away from the anchor. This can get into weird issues, and this is why we believe that the performance is not actually very good for the summation inside the log. Right. So what do the gradients like? We haven't trained any models yet. We've just looked at what the loss function should look like. We have done some few experiments. What do the gradients already tell us? This tell us definitely that hard negative and positive mining is already being done by the model. You don't have to do it manually, which is a very good thing if you are interested in implementing and productizing these models. Uh, the second is that everybody talks about that larger batch sizes help. Well, larger batch sizes have always helped deep learning because they stabilize the gradients. But why do they help contrastive learning more than cross entropy? And the answer is that since a large amount of the gradient is determined by what is this probability P of IP, if you actually end up getting a hard negative, right, or a hard positive, that is going to have a very large amount of contribution in the gradient. So larger batch sizes also increase the probability that you end up hitting a strong positive or a strong negative for your given anchor. And we don't know of any work that has actually tried to argue it this way. And we have an analysis in the paper which actually goes through the procedures of these results and shows how you come down to this. And I would encourage people who are interested to read that and maybe expand on those ideas. Right. So the most interesting part for a lot of people, that's the results. Not for me, I like the theory more. So we have amazing numbers, I would say. Firstly, we were able to get state-of-the-art numbers on ResNet 200 with both cross entropy trained with auto augment and stacked rand augment, and we were able to get state-of-the-art numbers on ResNet 50, 101, and 200 using supervised contrastive trained with various augmentations. And I'll go into details of that if anybody's interested. So, but overall, the picture looks like this. Irrespective of augmentation and more complicated techniques, supervised contrastive gets you better performance. Cut mix here is not exactly a standard augmentation in the sense that it actually mixes samples. So it uses label information more meaningfully, but contrastive learning actually does better than that. So that was interesting to me because I was surprised by that result. Um, we see consistent improvement across models and across data sets. So we're better than SimClear, which is unsupervised, cross entropy, which is supervised, max margin, which is also supervised, and then supervised contrastive is better than all of them for CIFAR 10, 100, and ImageNet. Then this is a more detailed version of the results that we have. And so on top 5 we have a state of the art number used on ResNet 200 with the augmentation stacked rand augment. And I can go into details of what this augmentation really is later. But basically it's just a more stronger augmentation than rand augment with color jittering and blurs. And and we also have similar numbers using auto augment on ResNet 50. And the key takeaway here is that if you have a larger architecture that helps supervise contrastive, if you have more stronger augmentation for those larger architectures, even then it helps supervise contrastive. Smaller architectures can get into trouble with stronger augmentations, but um, supervised contrastive helps against cross entropy anyway. Right. So this is all of this is on ImageNet. The question is that the entire point of doing all of this is that can you actually generalize? So and by generalize I mean generalize on different data sets. So we have this transfer learning benchmark, which is the VTab benchmark. We choose a small number of tasks. So what we have here is a model that is trained on ImageNet and then is fine-tuned on these specific data sets such as CIFAR 10, 100, pool, Sun 397, VOC, and you can look at details of that in our paper as well. And the key idea here is that first that we are competitive with most of the state-of-the-art models, which are cross entropy and SimClear on both ResNet 50 and ResNet 200. But the interesting part is that permutation significance does not exist between cross entropy and supervised contrastive. And our running hypothesis there is that for classification tasks, if you're training on ImageNet, the architecture is actually more important than the technique with which you're learning, but we could be wrong about this. And yeah, we haven't seen any interesting results which suggest that this is entirely untrue. Um, and that's after tuning, right? Without tuning, you could see differences. But we did see differences on the COCO data set, and we do see that supervised contrastive does much better. And this is like a very recent set of results that Yonglong has come up with. Um, and basically, we see that compared to other uh, tasks. So this number is not state of the art on COCO with like larger, with like other training techniques actually get much better numbers on COCO, but this is specifically comparing to other supervised techniques, and we do see that supervised contrastive does better. Um, right. Uh, we also see that we are actually much more robust to corruptions in the data set. So if you take the ImageNet test set and you actually corrupt it at various severity levels, as has been suggested by work done by Dan Hendricks, you can construct this ImageNet C data set, and we actually measure performance on that. So in the most important metric, in my opinion, is relative MCE, which measures the relative drop in performance with higher corruptions and severity levels. And we have state-of-the-art results for ResNet 200 and ResNet 50. You can also see this curve, which clearly shows that we are better than cross entropy. So the purple curve is ours in both of these cases. The dotted is ResNet 200, of course. Um, we also do see that we are much more stable to hyperparameters. One of the most important hyperparameters in contrastive learning is temperature, which we show here. But we do see that any temperature choice between 0.04 to 0.11 is mostly getting us near state-of-the-art performance. And we are working on trying to make sure that you don't have to tune the temperature so much. Of course, we also see that even at smaller batch size, supervised contrastive continues to do better than cross entropy. And this was a question that was raised by a few people that do you think that at lower batch sizes is want? No, the answer is that even at lower batch sizes, we do better. And this is like a 256 batch size, a 512 batch size, which you don't need TPUs or anything to train with that. And we also experimented with various augmentation schemes. So we have much lesser variation in performance with augmentations. You can change all sorts of augmentations. The augmentation used during pre-training, in the contrastive stage, you can change the augmentation used for training the linear classifier, and so on and so forth. But we do see that the performance is that doesn't change a lot. And same thing holds for optimizers. On learning rate, I would say the jury is out. Right. So learning rate changes we are susceptible to, especially learning rate changes in for pre-training. So you do need to tune your learning rates for contrastive learning still. But our hope is that one day you won't have to. Right. And one of another set of interesting results is that at small percentage of data, when you actually let's say take only 1% of your ImageNet training set, but evaluate on the full test set, what is your performance? And we realize that supervised contrastive does much better. So this is top 5 performance, and we get 57%, which is compared to the 38% of cross entropy, is just much better, and that holds throughout till 100. So it's a log chart on the x-axis for percentage of data. And we just think that we do better because we're learning more meaningful representations. Right. Um, there are a few downsides to contrastive learning, specifically for people who productize models, that it has a long training time. You need to train for like 350 epochs. We've often trained for 1,000 epochs as well to push performance, even though it doesn't lead to great results, but you have to do that. You can mostly get good results with cross entropy, which is state of the art if you have the right parameters in 100 to 200 epochs. So we are much longer than that. Larger batch sizes help us a lot. So if you want to get state-of-the-art performance, you want to use large batch sizes, and that gets problematic from not just computational reasons, but sometimes the network size is just too large because you're working at very high resolution images. So that's another problem. And then there is multi-stage training, and you need to decide, if you want to update your batch number parameters or not, and what's the momentum that you want to use. So this is just another set of parameters that you introduce. So that's definitely a very big downside of contrastive learning. And just very quickly, kind of things we're still working on, bunch of things, and other people should also try these things. That's generalized, the supervision for contrastive learning, no reason to just use ImageNet labels. You can also do out of distribution detection and maybe even classification free out of distribution detection, if that makes sense. And building stability to small perturbations in input data, that's something we're working on. And learning representations from multimodal data, which is learning similarity between text representations and images, text and videos, videos and speech. All sorts of combination exist, and people have already started doing this. I saw a few papers around which are coming up since this went up on archive. So yeah, I think very interesting. And yeah, of course, there are other contrastive learning techniques which have worked really well, and that is there's the MoCo paper, and then there is right, there's the DeepMind paper as well, and BYOL and so on. Then they have shown that if you use momentum encoders in memory, interestingly, then you can work with very small batch sizes and you can make things work. And while some of that work has been increasingly focused at unsupervised or self-supervised, we do believe that using label information would give you state-of-the-art performance when combined with those techniques. So we are trying a bunch of those things, but yeah, the people who are definitely productizing their models, they should look at if they want to try things like that. Right. So I think I'll stop here, and I'll just take a bunch of questions.
Nice. That was really good. Thank you. I have a question to get us started, and I'm sure Charles has a bunch too. So you talked about how your technique does better with larger batch sizes, but also most people don't have the compute resources if they have a big model to use large batch sizes. What's your advice for people to use self-supervised, like supervised contrastive learning in that scenario?
Yeah, I think memory is definitely your friend. So if you can actually keep, so the way memory works, it keeps a few scale representations.
Sorry, I think your audio is being a little
weird. Can you hear me now?
It's like breaking like that. Kayla, do you have any advice on how to fix it?
I don't. Maybe just pause your video for a second. It might just be a bandwidth issue.
Yeah,
sure. Stop video.
Sorry about that.
No, it's okay. Can you hear me better?
Better, yes.
Okay. Okay, let's just try this for a couple of minutes. Okay. So, right. So basically what I was saying was that memory is your friend there, because what memory allows you to do is keep a few scale representations around and you can contrast against them. So that's like a pseudo larger batch. The main problem with that is that since your representations are stale, when you're in the early stages of training with large learning rates, you can be really out of sync. But there are trade-offs that you can come up with. So memory is definitely your friend. And I would say that people have even tried keeping the entire data sets representations in memory, and that is doable because that's the reason why the representation over which you apply the contrastive loss is like 128 or 256. So that optimizes your memory. So that's one good reason to actually keep so small. Yeah.
Cool. And if people can start dropping their questions in the chat, and also the folks on YouTube, I know you're like 30 seconds to a minute behind. So just if I wasn't clear, please start dropping your questions in the chat. Charles, you had a question.
Yeah. So really cool talk, really interesting stuff. The contrastive learning approach is one that I'm really excited by, and it's cool to see them like people continuing to push the envelope there. So first, you mentioned that just for general contrastive learning, there's this interpretation of maximizing mutual information between views of the data. So just to make sure that I understood that right, you mean maximizing the mutual information between your latent representations, right?
Yeah.
And you achieve that basically by pushing those together and then pushing the other ones apart.
Yeah. Yeah.
Any
Exactly.
these like whatever your negative examples are. So
Right.
there's like, in my mind, that immediately brings up these like positive negative sample algorithms that people use for like wake sleep algorithms, right? The way people train maximum likelihood models, like Boltzmann machines and things like that.
Yeah.
So is that
Right.
is that more than an analogy? Is there a direct connection there? I wasn't able to figure that out.
Yeah. We haven't figured that out as well. Like I wouldn't say that there is a direct system there, but yes. So more intelligently sampling your positives and negatives, and actually making sure that your data views are constructed intelligently. If by that I mean that you make sure that there is not a very large amount of mutual information between those views, so that when you actually maximize the mutual information between those views, you actually end up retaining only the semantic information. That is definitely a very strong part of contrastive learning, and we do think that pushing on that helps. Even though random data augmentation is like a close proxy for that, there is more work to be done on that front, I believe.
The other question that I wanted to ask was, outside of the image setting, do you expect this contrast, like how well do you expect these kinds of contrastive learning approaches to work? For two reasons. One is a lot of image classification tasks basically involve these kinds of like texture and pattern matching things that maybe don't transfer super well when it comes time to do segmentation or depth mapping or something else with images. And then second, outside of like using images for your task at all, we're relatively limited in the kinds of augmentations we can apply to something like natural language processing, where it's somewhat difficult to come up with a reasonable data augmentation that maintains semantic meaning. So like, I don't know the literature very well on this. So like, do you know examples where people have done this before? And do you think, is your intuition that this will spread really nicely to these other domains?
Yeah. So segmentation is definitely something that the same backbone that it can be used for classification can be used for segmentation. So segmentation is something that can be handled. Other ones, it's not so clear. People haven't shown these things. But moving to non-image data, text is definitely hard because data augmentations are difficult. But you can come up with sampling procedures which construct your batch interestingly, so you don't have to do any data augmentation. Because technically, see, if you don't have any data augmentation, even then contrastive learning does work because it is still pushing samples from the same class together and another class apart. And so for text, intelligent sampling helps. Audio is a signal. You can perform very interesting data augmentations on audio signals, so I'm not that worried about audio. There has been work which actually is like basically the equivalent of ImageBot, which shows that you can actually learn similarities between text and images, and there they do use image augmentations. So I do think that contrastive learning would be able to extend to such settings.
Yeah, so you mentioned, so text classification, you still have this nice class label that helps you figure out which things are similar and which things are not. But maybe something like machine translation, it might be difficult unless you have access to, say, multiple translations of the same sentence that would allow you to maybe do data augmentation that way.
Yeah, no, for sure. Yeah, for machine translation, it's not very clear how to make that work but yeah, I mean, some people have the perspective that why do it because basically already what we have, the transformers already work. So, but yeah, I mean, I don't have a very good answer for
that. Someone in the comments. Oh, wait, Charles, were you done?
Yeah.
You can keep going. Someone in the comments asked, can you apply this to deepfakes? Because they're working on deepfakes and excited about trying this technique.
I do think that it's worth a try, but we haven't done it, so I won't say yes because I don't want to be held liable for that. Right. Statistical regularities and irregularities is not something that I expect contrastive learning models to be very good at, because strong data augmentation actually normalize for that. So I would actually expect that they would just learn to ignore a lot of statistical irregularities. And if deepfakes are actually using those statistical irregularities, then it's possible that we're not able to handle that. And yeah, so I won't say for sure that it would work.
All right, someone
I
else.
did have actually another question.
Yes.
Yeah. So, are you familiar with slow feature learning? It's like it's sort of a pre-deep learning approach. The idea is, if you have like video data and you want to learn, like basically do image pre-training, what you do is you learn, you learn representations such that the features don't change from frame to frame, or they change as slowly as possible from frame to frame. So you have a term to keep the entropy non-zero, right? But then you also have a term to keep the covariance high. So this slow feature analysis idea has been used by a couple of deep learning type approaches, but it seems like a version of like contrastive learning without the contrast, right? It's basically just positive samples. But there might be some interesting ideas in that slow feature analysis world for contrastive learning.
Yeah, I think I agree with that. I do think that there is a very big space for contrastive learning, where what you do is you take video data and you have this graded notion of a label. So you have a graded notion of a similarity, and then you try to optimize for that. So you can basically have a weighted form of the contrastive learning. And I think people are trying this. I know of a few teams who are trying this. So the hope would be to see some slow moving and some fast moving features which automatically come up because of the structure of the loss.
Cool. Someone else in the comments asked, could you talk more about the augmentation techniques that you tried, and what makes supervised contrastive learning stable to these augmentations more so than other?
Right. Yeah, let me try and pull out something. Okay, so basically broadly the augmentations we cared about was auto augment, rand augment, stacked rand augment, and sim augment. So going through them, auto augment is basically the strategy which is trained. So you have to apply two augmentations, and you decide the magnitude of this augmentation and the order of that augmentation using a policy gradient learning algorithm which optimizes for the top one accuracy of ImageNet. Rand augment works slightly differently. You have a controllable parameter, and then you sample your pair of augmentations that you want to apply randomly. And the idea is that if you tune this parameter, which is like the magnitude of the augmentation correctly, you actually even beat auto augment. So basically, the idea is that even if you learn a policy, you can just actually randomize it and get the same thing. So if you don't have compute, you should just use rand augment. Then what we did with stacked rand augment was that we actually, and this was Longlong's contribution, that he basically figured out that if you take Gaussian blur and color jitters, and after applying color jittering, before applying color jittering, you actually do a rand augment. So before you actually apply the color jitter, you actually do rand augment, then you do a color jitter, and then you do a Gaussian blur, right? But this rand augment is applied after doing the cropping. So the order basically goes cropping, rand augment, color jitter, Gaussian blur. Then this is a much stronger augmentation and much more useful for contrastive learning. So that's basically what the stacked rand augment is. And sim augment is basically something that the Hinton paper introduced, and what they did was color jittering, Gaussian blur, random cropping, flips, and we had added something else on top, which was warping, which actually just shows 4 points and actually just warp the image. So the second part of the question was that, and I don't know if I got this correctly, that why do these augmentations work well for contrastive learning? And
yeah, essentially.
Yeah, so the idea basically there is that augmentations are supposed to spread a single data point in the representation space. So what that allows you to do is like you have now have like a denser epsilon ball in a high dimensional space for every point. So now this contrastive learning setup, what it allows you to do is not just that you're pushing away single points, you're actually pushing away this density, and that is more meaningful. So that's one good reason to use augmentations. The question is that why would one augmentation work better than the other? Um, the answer is not clear. We do think that denser is better. So basically, it's like this in this 2K space. How much can you explore using your augmentations? So the more orthogonal systems you have in your augmentation, the denser this epsilon ball is. But right, but this is basically an analysis, and it's not very grounded. Like we don't have a lot of experiments to back this up, but this is more intuitive in the geometrical space.
Gotcha. And is this also related to why supervised contrastive learning is stable to corruptions in the ImageNet dataset and to hyperparameters like temperature and stuff?
Right. Yeah. So we do believe that yes, since we're doing a much more meaningful representation learning system. So like okay. So the point is that even if you use the same augmentation for cross entropy and supervised contrastive is still better. So that means that it's not just the augmentation, but it is the fact that you're never able to pick up on spurious correlations between your labels and your representations, and that's just like a property of the cross entropy function, that the cross entropy function is going to try and best and minimize the loss, right? So
Yeah.
it will try to pick up spurious correlations, but since you have this dense ball and you're pushing these dense balls around, there's no notion of why you should pick up any spurious correlations, because it's not just about projecting this ball using a linear plane into the right class. Now it's about actually pushing away these dense balls and the 2K space.
Interesting. Cool. I think those are all the questions that I saw. Charles, do you have? Oh wait, there's more. Interesting. Someone said they want to start with AI and machine learning. They have a strong background in Python. At what stage should they be taking interest in subjects like contrastive learning? What should be their path? This is an important question, I feel like, because all these Coursera and Udacity courses do such a good job of like teaching you the fundamentals. But how do you go from there to like, picking up interest in something specific like you?
Yeah. Okay, I can describe the way I did things. Ian Goodfellow's book is, I think, a very good plus place. His book, it's available online freely, and you can just read that book and build your intuition, and then just start reading papers. So but yeah, you need to re-implement things on your own. So you need to have like a goal in mind that okay, you want to maybe re-implement very difficult GAN paper or contrastive learning paper or something, and then read through books and papers to get to a stage where you have the end-to-end understanding of each step and why you're doing it.
Gotcha. That makes sense. Cool. I feel like we've gone a lot more over time, but the questions are amazing, so I kept going. Thank you so much, Prannay, for coming. If you want, you should totally do an AMA in our Slack community, and you'll get a lot more questions there. And we'd
Okay.
love to. Thank you so much for. Oh wait, someone has another question, but we'll get to them later. Yeah. Thank you so much for coming.